And for our final presentation in session 4 today, we have Dr. Hadi Hunga from DLR as well, presenting methods for parameter space exploration. And Hadi, you are the team lead for processes and methods in the department Verification Validation. And at set level, you are the leader for subproject 1. We are excited to hear from you. The stage is yours.
Yes, thank you very much. I'm pretty happy to have this slot on the final event of set level. There's a co-author who contributed half of the content of this talk. That's Barbara Schütt from the SZI, the Karlsruhe Research Center for Information Technology. And yes, be prepared for a little dive into the scientific side of applying simulation, which is not all that simple if you got a complex task to solve, a complex test task defined by mainly a logical scenario, which we all know has many instances. And you would need a clever method to look for the interesting instances and simulate those and avoid too many meaningless simulations. Because such a logical scenario, even a small one, a simple one, defines a huge test space. And so I'm going to present you two methods. One is about speeding up the simulation to get to the interesting points in the test space fast. And the other is even more ambitious, not only finding the interesting instances, but also guaranteeing that we found them all. So the first one, fast coverage, is by Barbara. The other one is by me. Look at these. So look at the problem domain. We are given a logical scenario. Here's a simple one. The EU car coming from the bottom, this E-vehicle turns right, and there's a pedestrian who crosses the street, and there are two other traffic participants. And Barbara has chosen here 3 parameters of this logical scenario to vary, which are the starting position of the ego vehicle, the speed of the other car coming from the right, and the delay with which the pedestrian crosses the street. So there are some interdependencies, of course, and if we look at the full test space, well, given a reasonably fine resolution of the parameter spaces, we end up with some 600,000 instances, which potentially would have to be simulated to get a full understanding of what might go wrong in this scenario or what might be interesting in this scenario. This is a number which makes cloud computing providers happy, but us as users, appliers of simulation, not that happy, because we would have to wait for a very long time to get the results or pay very much money for that. We don't like that. And there are even more complex scenarios than this one. And so it gets very interesting to have a higher order procedure which tells us, OK, these are the interesting cases. This is a higher order procedure. I call this procedure like that, because it uses standard simulation tool, like the ones you've seen in the demonstration cases, which is capable of performing one single simulation run, that is one instance parameter combination, one concrete scenario, which is simulated and then evaluated with the given criticality indicator. And OK, building on this functionality, we propose 2 procedures with, say, complementing goals. OK, let's look at the first. The general idea is we do some simulations, start with a concrete scenario, do a simulation, evaluate it for here criticality, and then choose the next one and go on and go on and go on. And the interesting thing is, of course, to choose cleverly. And in this case, for Barbara's method, fast coverage, this is an instance of Bayes optimization with here Gaussian processes, as you can read. A little bit more detail on the next slide. Bayes optimization is a common procedure to find local maxima of a function which is unknown but can be computed at definitive points, just like we are doing here, using one parameter combination to get one concrete scenario which we can put into our standard set-level simulation tool and then look at the results. And here we have a little illustration of what goes on with this Bayesian optimization. We have made some, at the top picture at the right, some simulations. In this case, these were 5 red dots. You may be able to see them, which gives us function values of our criticality at these 5 points. And for the rest, we use a Bayes estimation of what goes on in between. And we see the target function, the unknown target function, aligned in black. And in blue is the current estimation with confidence intervals, so that is standard deviation depicted here. And we see, looking at the picture at the bottom, the more points we get, the better our estimation does get, and the smaller the confidence intervals do get. And in this way, by using this prediction, this extrapolation from the simulation results we have seen so far, using this prediction, we can choose interesting new points. Now, Barbara has even implemented this procedure and tested it on the simple scenario I presented earlier, and did some computations for 6 different criticality indicators. Side remark, there's no one-shot criticality indicator which tells you everything which might be critical in a scenario. Each criticality indicator she used captures the different aspects of criticality. I will not go into the details of these criticality indicators. Most of them are pretty standard and defined elsewhere. But in the end, we see more or less there's a diagonal through the parameter space. Here only 2 parameters are depicted. It's always difficult to make a depiction of the results of a 3-parameter computation on slide, which is only 2-dimensional. So, and in each case, the procedure was able to find the interesting points pretty fast. So it did not have to pay too much money to the cloud providers for providing this computation power to get to these results. So for this procedure, the experiment summary, we had potentially some 600,000 combinations to explore. And all in all, for all these 6 criticality indicators, there were only about 400 combinations necessary to come to the interesting points and also to see where it is not interesting. This is a pretty good result, tremendous speed up, so perhaps less than 100 simulations per metric, per criticality indicator. And you can read up the details in the paper, which is listed here on this slide. Or, of course, you can contact Barbara for more details. And there's also a booth outside where we presented some more technical details this morning. And there's future work concerning with that, building on the results which have been proved. And there are similar instances of the scenario of the critical situations which do evolve, but with completely different parameter combinations. If we modify the car speed and the pedestrian delay, then we come to the same situation between pedestrian and car, and to identify these and exchanges between parameter combinations, Barbara is working on extending the results and making an analysis of the scenario based on that, clustering the different parameter combinations, and so on. So this gives you then, or will give you, say, a testing procedure which gives you a handle on the test space, on the huge test space. And in my impression, it is a pretty good handle already. But if you want to use this for a proof that your car is really behaving in a safe way, that might not be enough. Then you will have to analyze very closely. And this procedure is not meant to give you a real guarantee that nothing has been overlooked. So let's go for a more ambitious, more involved, and, well, perhaps not really that yet practical method. One which tries to give you a guarantee that everything which is interesting, everything which is critical, has been seen in your simulation and identified. Okay, so setup is a little bit different, but again, we have an illustration with a two-parameter logical scenario space. On the right, you see lots of dots within the square. Blue ones are uncritical simulation runs. Yellow ones are, well, significantly critical, so you might want to look at them again, but not really highly critical. And the ones you really want to factor out are the red ones, the high criticality things. And of course, our criticality indicator is supposed to identify these by the values it produces on the simulation runs, on the single simulation runs. And again, let me stress, this function, this square, is unknown. We don't know where the red colors are. We don't know where the blue colors are. We don't know anything at the beginning. Okay, so to do that, to give a guarantee, we have to invest a little bit more into the setup of our simulation. In particular, first thing which comes to mind, our criticality indicator. If we want to give a guarantee that the high criticality is not overlooked, then this should not come as too much as a surprise to us. That is, our criticality indicator should not jump from 0 to 1, of course, but should indicate, okay, we are nearing an accident, and it should give an indication of that by giving us a value indicating significant criticality. And no jumps, that is, we want to have it smooth, that is at least continuous or even continuously differentiable on the trajectory space, on what happens on the street. And then, if you remember mathematics analysis first semester or so, if you were forced to take this course, there was something like Lipschitz continuity, which gives you an estimation of how much a continuous function will change in a local neighborhood. So this is one of the basic main ingredients we use here. And we can do so because on the trajectory space, that is what happens on the street. And trajectories, if I change parameters a little bit, trajectories changes. But usually you would not expect that trajectories will change very abruptly. This is physics. Natura non facit salta. So a car, if it accelerates, yes, trajectory will change, but only to some degree. It will change smoothly. And also, if we combine trajectories, and one changes a little bit, other changes a little bit, then criticality might increase, but not abruptly. So we can spot this. This is the very idea of being able to have a continuous indicator of criticality on our trajectory space. Okay, so we got the simulation space, the logical scenario, we got the concrete instances, we got the criticality indicator, so we got our target function, and we want to, say, identify the red spots, and of course it would be also interesting to identify the blue spots as well, because you don't have to think about them ever again. And so mainly we can reduce. We want to cover the red dots conservatively, that is, include everything in one defined region, identified region identified by our simulation procedure, which is here are all the red dots of our logical scenario. So, and you can imagine continuity helps us because making little changes on the trajectories does not change the criticality too much. Okay, so we got rid of potential uncontinuities of our criticality indicator, but there's one or two types of discontinuities we cannot get rid of. These are buried in our test space. They are defined there. Let us return to this right turn example of our ego vehicle. There will be parameter combinations where the ego vehicle passes before the pedestrian is close or enters the road at all. And by modifying these parameters, we will come to a point where the pedestrian crosses and our car hopefully stops and does not overrun the pedestrian. And between those two discrete forms of behavior, there will be a border in the parameters where our ego vehicle takes the decision not to pass before the pedestrian and to wait, or the other way, to go through. So these are things where our ego vehicle makes some decisions which lead to abrupt changes in the trajectory space looked from the logical scenario. And also the other traffic participants, if they are agents, they will have their decisions and change their behavior depending on the situation observed. These are also potential uncontinuities in our parameter space. So, and you see in our two-dimensional parameter space, I've drawn some black lines indicating where other traffic participants cause a discontinuity, and red lines where our ego vehicle does something which changes abruptly the trajectory observed. So, yeah, how to cope with these discontinuities we cannot get rid of? Well, following the strategy, know thy enemy, we identify them. So we look at all these potential sources of discontinuities and we measure them. One thing is in the scenario description where traffic participants make a decision causing a discontinuity, we have a handle on that because we can see the triggers which let our agents change their decision. We have, at least I assume that here, in the scenario definition, I can see where there are discrete decisions taken by the other traffic participants. What I perhaps cannot see are these discrete decisions of the ego vehicle. And yes, I would have to rely on observation, this I can always do, and also, of course, on additional, say, test outputs, which this highly automated driving function in the ego vehicle does. And with that, I measure all these borders between continuous regions and have reduced the problem of covering one continuous region where I have a Lipschitz continuous function. Well, that's great, because Lipschitz continuity gives me a guarantee that one simulation run is representative for a local neighborhood. And I can delineate the size of the neighborhood by the Lipschitz constant. The criticality indicator will not change too much, that is from uncritical to high critical, within a given space around my concrete evolution I have seen. So this gives me something like the green circles with the dot in the middle, which is the representative run. And the same, very much the same I have for the critical ones. I can see, okay, here I am critical, and I know all the local neighborhood are at least significantly critical, And then I can cover also the identified critical regions. And if I collect enough of these representatives and local neighborhoods of them, I can cover, at least in my mind, let's see how it works out in practice in the computer, I can cover all the scenario space and have some sort of guarantee that I haven't overlooked anything of interest. Of course, making some assumptions about the higher order in the driving function, not making some strange things, having glitches on some bit changing in the situation, representation, and the behavior will be completely different. I would rely that all these glitches have been ruled out by following a well-designed development process, as it is required for such a complex and safety-critical function. So, and then I can hope to be able to identify all the continuous regions sufficiently well and cover all these regions, and up with a guarantee that nothing has been overlooked. So, to sum up, what have you seen? Two procedures coping with the interesting problem, complex, difficult, computationally expansive problem of covering a large scenario space. One of it, which is clever, goes to the interesting points fast, hopefully getting all of them. And if you want more, there's a more involved procedure, more expensive, I'm pretty sure. It's not fully implemented yet. It's in the early stages of implementation. We'll continue that in VV methods, which gives you some kind of guarantee. Let me say the best I can imagine currently for this test problem of a large scenario space. And yes, we have a fast procedure which is implemented. We have a more complex one which is going to be implemented. But let me stress at the end, exploring these last test spaces will never be easy, and the cloud providers will be, I think, rather happy with all the computing power we will buy from them. So, thanks a lot for your attention.